So our good friend Ludwig here decided that he wanted to investigate entropy, and he wanted to try and describe entropy using an idea that he called microstates. He tied this idea of entropy to the concept that you could take molecules, and if you captured them in a moment in time, all the molecules and atoms in a system would have several different ways that they were moving around inside of the system. So they would have translational movement. This is movement of the entire molecule from one place to another. They would have vibrational movement, which would be the periodic motion of atoms within a molecule. So, for example, here the water molecule is moving where those hydrogens are kind of going back and forth, back and forth, back and forth, back and forth, both of them like that. They also scrunch up this bond and that bond. So there's multiple different ways for them to vibrate, and each one of these has a different frequency associated with it. And there's also rotation that's occurring with any of these molecules. So you could have the molecule spinning around an axis. So there's lots of different ways for molecules to be moving in a system. Lots of different states for them to be in a system. And so Boltzmann envisioned this motion of molecules of a sample at a particular instant in time and said that snapshot is a microstate that is available for the system. That is one possible way for the system to exist. And if you take another snapshot a moment later, those molecules will probably be moving a different way. They'll be in a slightly different position, they'll be vibrating slightly differently, they'll be rotating slightly differently. They will be in a different microstate. And so he envisioned entropy being associated with the number of available microstates to the system, the number of possible ways that molecules can be moving around, can be rotating, can be vibrating, the number of ways that they can distribute themselves, essentially. And so the equation that he used to quantify how much entropy a system had is this. So S is the entropy, K is the Boltzmann constant, which we will find in lots of different places, actually, not just in this equation, but this will be where we mostly see it here. If you go on to higher level chemistry courses, like I believe in PChem, it comes up quite a bit, PChem being physical chemistry. There's quite a bit of thermodynamics in physical chemistry. But anyway, so K here is a constant, it's the Boltzmann constant, which is this value right here. And then you have the natural log of W, which is the actual number of microstates that a system has available, the number of ways that a system can arrange itself. Most of the time, though, we're not interested in quantifying the absolute entropy. Sometimes we will, and I think you will do that in one or two of the homework problems. But most of the time, we're actually interested in the change in entropy, not in just the absolute entropy. And so to get the change in entropy, since entropy is a state function, we can make a slight modification to the equation from back here, and we can have the change in entropy is equal to Boltzmann constant times the natural log times the final number of microstates minus the Boltzmann constant times the natural log of the initial number of microstates. And we can do a little bit of algebra to that to simplify it to this equation here. And this is the one that's usually used, just because it's a little easier to work with. So, as the number of microstates increases, so the final value being larger than the initial value, then the entropy will increase. So the number of ways for a system to arrange itself, if that increases, entropy increases. So, how can a system increase its entropy? There's a few different things, a few different properties that have an effect on the number of microstates that are available, and therefore the entropy as well. So temperature, volume, and the number of independently moving particles, as each of these things increase, the number of microstates that are available to the system will also increase. So with temperature, for example here, as you heat something up, actually let me see here. Yeah, so we're heating this up as we go from a solid to a liquid to a water. Things will tend to become, well, not tend to, they will have a higher entropy as you go from one to another. Both just because the temperature is increasing, but especially when we get these phase changes, the entropy will increase quite a bit. So when you have a cold piece of ice, the molecules there are really held in position. They can't move around very much. They're not completely restricted because they can vibrate, and every once in a while they might be able to rotate. There is some rogue movement of stuff inside of crystals. That's a very common thing, but for the most part it is mostly just vibration. So there's not very many microstates relative to the other two phases anyway available for ice, just because the movement of the molecules is very restricted. When you heat that up, you turn into liquid, and so not only do you have more entropy just because it's warmer, which would then increase the vibration and the rotation of molecules, but now they're no longer held in a crystal lattice. So you have liquid water here where the molecules are free to move around. They can translate freely with respect to one another, and now they can also rotate freely. So they could vibrate before, but now they're also rotating without any trouble. But they're still kind of held in there together. There's still restrictions on the amount of movement they can have. They really lose most of their restrictions though when they go into the vapor phase. So if you heat them up even more, they go into the vapor phase. Gases have much more entropy than either of these two, but especially a lot more than the solids. Gases, if you have 1 mole of gas, that probably has more entropy than several moles of liquid, just depending on what the molecules are. So you have complete freedom of translation, vibration, and rotation. There's a very large number of microstates available to gases. So as you heat things up, because they have more energy, they have more modes of vibration and rotation available to them, and they, especially if you heat them enough to go from one phase to another phase, you will most definitely increase the entropy. If you increase the volume, you will also increase the entropy of a system, because you're essentially opening up new spaces for things to go to. You're allowing them to spread out even more. Because remember the way we were describing it before is if there's more ways for the energy to be spread out, more ways for the molecules to be spread out, more possible places for them to be, that is a higher entropy system. And so if you give them a larger volume to move around in, that is going to be an increase in entropy. And then the last one there, the number of independently moving molecules. This should make pretty much logical sense here. If you have 2 moles of gas and they're moving around, and then you add an extra mole of gas, you're going to have more entropy because you have more particles. There's a whole bunch of new particles. They're all vibrating, they're all rotating, they all are in different places than all the other ones because none of them can occupy the same space anymore. So if you have more independently moving molecules, you will have greater entropy. Alright, and we already talked somewhat about this as well, that as you move from one phase to another, you are going to have an increase in entropy. What we didn't really discuss, though, is that these phase change processes here are what we call isothermal processes. We did talk about this in a previous chapter, but not in this chapter yet. So if you remember from, I believe, the first chapter, I think, that we talked through in this class, we talked about how when you increase the temperature of a molecule and it starts to go from one phase to another, when you're just increasing the temperature and the phase is not changing, you have this region here where the heat that you're adding in is increasing, but at the same time, you're increasing the temperature. But once you get to the phase change, you are still adding in heat, but you're not increasing the temperature. And so what you're doing there in these regions is you are melting and or vaporizing, just depending on which region you're in here. So down here you'd be melting, and up here you're vaporizing. You're vaporizing the material, and that energy is not going into increasing the temperature. You're still putting heat in, but it's not going into increasing the temperature. In these phase change regions, we are increasing the entropy of the system. We're breaking intermolecular bonds, we're pushing the molecules away from each other, we're increasing their entropy as we're doing that. And so these isothermal processes, when they happen, we can actually quantify the entropy change that's occurring using either of these equations here. These are essentially the same equation. It's just here we have enthalpy and here we have heat. And if you remember, the only difference between the two is that enthalpy is defined to be at constant pressure. So other than that, they are exactly the same. So the entropy change of the surroundings, and you do need to note that this is the surroundings, not your system. The entropy change of the surroundings is going to be equal to negative the enthalpy change of the system divided by its temperature. And we'll have a question or two in the homework where you will need to use this equation to find the entropy change of the surroundings, or perhaps to find the enthalpy change of the system, just depending on what the question is asking you for. Alright, so I think in the next video here we will talk about solutions and some interesting things that can happen with entropy changes in solutions, and we'll talk about how we can predict the entropy change for processes just by looking at the reaction that's taking place.